Okay, hello everybody. Today we're doing the central limit theorem. So the central limit theorem looks at the distribution of sample means. So what does that mean? Well, if we have a normally distributed quantity, it may be heights of year 12 students, then if we take samples from that, say we're taking sample sizes of 2, so we select 2 different measurements from that population, and then we can find the mean. So sorry, let's just do that again. So we're going to select 2 measurements, and then we're going to find the mean from those 2 measurements. And if we repeat that, say 5 times, we're going to start building up a distribution of all the means that we've collected from our samples. Now, when we project that further and do that 10,000 times, you can see that we get an entire distribution. So when we're looking at the central limit theorem, though, we're not only going to be looking at populations which are normally distributed, but we could be looking at any particular distribution that may be uniform, it could be skewed, or it could be one that I've made up myself. So if I just drag my mouse, we can create sort of a crazy type of parent population histogram, and then we can select 2 measurements from that and find the mean, and then perhaps do that 10,000 times, and we get this sort of crazy distribution. But we don't actually have to take sample sizes of 2, we could do sample sizes of 5. Or so we can take 5 different measurements and then create a histogram out of that, and then if we do 10,000 different samples, all of 5 measurements each, then we create this kind of distribution. And we could increase our sample size, so we could have a sample size of 16, where we're taking 16 different measurements and then finding the mean. So we'll just let that happen, and then we could repeat that 10,000 times. And you notice with both when our sample size was 16 and when our sample size is 5, we seem to be getting a distribution that's normally distributed, or approximately normal. So if we fit a normal curve to that, you notice that the histogram represents something that's actually quite normal, whereas our parent population wasn't normal at all. So we could try that, say, with a uniform distribution, so where pretty much the histogram, the bars on the histogram have the equal height, and we can start at, say, take sample sizes of 5, and then so 5 different measurements, finding the mean of those, and then if we do repeat that 10,000 times, we actually get something that's quite normally distributed. We could also try it when our sample size is 25, so taking 25 different measurements and then finding the mean from that, and then repeat that 10,000 times. It's interesting to note that we get something that's actually very or approximately normally distributed. And we can also see if we take a skewed distribution, again, start at, say, have a sample size of about 10, so we take 10 different sample sizes and then use that to find the mean of that particular sample, and then repeat that for 10,000 different samples. We get something that approximates quite well to a normal distribution. And then if we go up to, say, where our sample size is 20, so taking 20 different measurements, and then from that finding the mean of that sample of 20, repeating that for 10,000 different samples, we get something that is again fits nicely to a normal distribution. So what the central limit theorem basically says that, well, it says that if you take many sufficiently large, random samples, and we won't fill that in, I'm not exactly sure what's supposed to be there, but if many sufficiently large random samples are taken from a population of any shape, that's very key that it can be any shape, then the distribution of sample means, which we're going to represent by x with a bar over the top, so you remember that we represented the distribution by a capital X. Here we represent the distribution of the sample means by a capital X with a bar over the top. So the distribution of sample means is approximately normal. Now, we want to have a look at the mean of this distribution of our sample means. So, sorry, just allow me some time to find the right page. So if we have a look here at our parent population, we notice that the mean is 8.08, and the mean here is 8.08 as well. So that's for our sample size of 20, but say we had a sample size of 5, we notice that it's 8.10. If we have a sample size that goes up to 25, we notice that it's 8.10 as well. So this is demonstrating that the mean of our sample means, or the mean of the distribution of sample means, is very similar to the mean of our population. So just to formalize that, we say that the mean of the means, which we're going to represent by mu of x bar, so that's the mean of our means, is constant and is equal to the population mean. Which is just simply mu. Now, going back to this simulation we've got here, we should notice if we just take some custom distribution, doesn't really matter what, then if I just take sample sizes of 2, so that's where we're taking 2 measurements, finding the mean, and then I get my distribution, you should notice that the spread of this histogram is quite large. But then if I go up to somewhere like 16, and then so I'm taking 16 different measurements from my population, then finding the mean, then for 10,000 different samples, you will notice that the spread of our histogram has decreased quite dramatically. And then if I increase that to 25, the spread of our histogram for sample sizes of 25 has reduced as well. So as n increases, we saw initially that the approximation to normality improves, but we also notice, and we also notice that the standard deviation of the means, which we represent by sigma of x bar, decreases. So there's this inversely proportional relationship between n and our standard deviation of our means. So to just formalize that officially, I'm just going to quickly add a text box there. We notice that the mean of our sample means, which we represent by mu of x bar, is equal to our population mean, mu. And then also we notice that the standard deviation of our means is equal to sigma over the square root of n. Apologies as I just fix up the formatting here. So the mean of our means is equal to the mean of the population, and the standard deviation of the means is equal to the standard deviation divided by the square root of n. That can be mathematically established, but we won't do that here. Okay, so you might be wondering how large n should be before the central limit theorem can be applied. It depends on many factors, and if the population is skewed, it may require quite a large sample size, but if the population is symmetrical, a small sample size is really sufficient to use the central limit theorem. So we can notice that here that if we take a skewed distribution and then we have sample sizes of 5, then we notice that this skewed distribution is affecting the skew here, so we need to go up to something more like 25 and we get something that better approximates a normal distribution. Whereas here, if we take something that's symmetrical, so a normal distribution, and we do it for something as small as n equals 2, then we notice that that's already normal there. So when can we apply the theorem to small sample sizes or small samples? Well, if we know that x bar, so the distribution of our sample means for a smaller sample size, is already approximately normal, then small sample sizes are going to give us an x bar distribution which is approximately normal as well. So it's going to be fine. Also, in the special case where the population is normal or normally distributed, then the distribution of x bar is going to be always normal, and so in those cases the sample size, we can apply the central limit theorem to those sample sizes as well. So the key thing to remember is that when we're using the central limit theorem, we're concerned with the distribution of the sample means, not the distribution of individual data. So what does that basically mean? Well, that basically means that when we're using the central limit theorem, we're not looking at this histogram, we're looking at this histogram. Okay, so the central limit theorem is quite powerful because it allows us to use normal probability calculations so that's what we've been practicing this last week, to answer questions about sample means from many observations, even when the probability or the population distribution is not normal. And so for that reason, it's quite powerful. So basically, to summarize what we've been looking at, the central limit theorem states for a sufficiently large n, the distribution of sample means is approximately normal. And we represent that by x bar. So it's approximately normal with a mean of mu, where the